right, thank you very much for the invitation. It's a great pleasure to be here, and now we're going to switch gears and talk a little bit more of the fundamental side, but applied to atomic sensors in general. So I'll tell you today about some of the experiments that are happening at Stanford in terms of quantum metrology, and I'll quickly flash this slide, and here I am, and this is the team, our principal investigator Mark Kasevich and the two graduate students, Nils Engelsen and Rajiv Krishnakumar. Everything I'll talk about is done in collaboration within these four people. So the big question we ask is, how can we control and exploit quantum correlations in large atomic ensembles? And in particular, we like to study and engineer entanglement in these ensembles, and with a very specific goal in mind. We would like to improve the already best performing atomic sensors that are out there. These sensors, be it atomic clocks or be it inertial atom interferometry sensors, they typically run at the standard quantum limit and also at the atom density limits. So if you want to improve these sensors, you cannot really increase the atom number to get the precision higher, but quantum entanglement offers you another path in this direction. So the talk will be composed of 4 parts. I'll briefly get you up to date with how we describe these quantum states of atoms, and I'll just give you a brief overview of quantum metrology, in particular spin squeezing. And then I'll go ahead with describing our experimental system, which is cavity quantum nuclear dynamics, and I'll present you some squeezed state experimental results. And very briefly at the end, I'll talk about a very new experiment where we do quantum phase magnification. I'll come to that. I'll explain to you what that is. All right, so here's a formal view of atomic sensors. So let's say you have n two-level atoms. You can simply describe these by n spin-half systems, and in our experiment, this is going to be the hyperfine clock states of rubidium atoms. And we take all of these spin-halves and put them together, and we get ourselves a spin n over 2 system. So it's an angular momentum system. So then we describe this with the projections of the angular momentum. Here the JZ axis corresponds to the population difference between these two states, and where you are on the equator corresponds to the phase difference between these two states. And here you see an uncertainty area on the state. This is a quasi-probability distribution in a sphere. So that comes from the fact that different components of angular momentum do not really commute with each other. So you get a Heisenberg uncertainty principle between different components of this angular momentum. So the typical word shot noise or standard quantum limit corresponds to this JZ measurement, where you're making a population difference measurement between your two different states, and you're getting the square root of n uncertainty on these states. So as long as you obey the uncertainty principle, there is nothing that's preventing you from squeezing one of these directions to get a better precision in your measurement. And this turns out that this necessarily implies entanglement between atoms. So here's a generic atom sensor that we all know how a Ramsey sequence works, but I'll go briefly over the sequence to show you the difference between the squeezed states and non-squeezed states. So you start with all atoms pointing in the down direction, and then you apply a pi over 2 pulse to bring them on the equator of the Bloch sphere, and then there's an unknown signal that's going to accumulate on your detector and cause a phase shift. And then you want to measure this phase shift, and you make a rotation and map this phase shift onto population difference, and then you go ahead and read it out, and there you go, you measure the phase. And with uncorrelated atoms, you reach the standard quantum limit to phase resolution, which goes as 1 over the square root of the number of atoms, as I already mentioned. So with squeezed states, the only difference is that you do an initial preparation where you prepare your squeeze states, and then it's a plug and play method. So you put your initial squeeze state, and then you make it into a phase, you bring it into a phase sensitive orientation, and then you again let the unknown phase shift act on your system, then again you turn it around and measure the population difference. So it goes the same way, but there's just an additional step, initially preparing states. So with this, as is clear from pictorial, you can resolve better phases using this, and in principle you can go all the way to the Heisenberg limit, which goes as the 1 over the number of particles that are involved in your experiment. So very quickly, I want to tell you how we measure squeezing in terms of how we quantify it, and tell you that there are other physical systems out there, and then I want to move on to the atoms. So, to characterize squeezing, we quote the reduction in the variance of the noise. So this turns out to be the relevant number. So here's a chart that converts dBs to normal numbers for those of you who don't like dBs. So for example, if you have 20 dB squeezing, that corresponds to a reduction in variance of a factor of 100. And what that buys you is that you can do the same, you can achieve the same measurement precision either with 100 times less averaging time or 100 times less atoms, for example, or corresponds to increasing your atom numbers by a factor of 100. So squeezing has been investigated in a variety of systems, including superconducting circuits, mechanical oscillators, and as a matter of fact, it has been implemented in LIGO in the last couple of three years ago. But to date, or prior to our experiments, the record-holding squeezing was 12.7 dB, which corresponds to a little bit about 10 improvement. So I'll tell you about atoms now. So, and then I'll tell you more about how other people are doing as well with atoms. So we want to generate squeeze states of atoms, spin squeeze states, and the way we do this is basically a measurement-based method. If you can make a measurement on the collective state of this ensemble of atoms, you can in fact project the quantum state of the ensemble into a reduced noise state. So we make a measurement, the state of the ensemble gets collapsed onto a spin squeeze state. That's how we're going to do it. And the way physically we accomplish this is, the simple version is we send a beam of light through the ensemble. Depending on which hyperfine state the atom is, it sees a different index of refraction. So it puts on the light a phase shift that's proportional to the population difference between the two atoms. And if you go ahead and measure that phase shift, state of the collective state of the atoms collapse into this squeezed quantum state. We don't do it this way. We put all the atoms inside of a cavity, and 175,000 finesse optical cavity to make the light go through the ensemble over and over and over again so that we increase the interaction. Furthermore, from one side we send a 1560 nanometer optical light that's going to form a standing optical wave inside of the cavity to trap the atoms. And then from the other side, we're going to send in the light that's going to probe the atoms. And notice the frequency doubled relationship here, that wherever there's an atom sitting in the optical trap inside of the cavity, you have a maxima of the probe intensity. So here all atoms are identically and maximally coupled to your cavity, and you're probing them with complete uniformity and maximal interaction strength, which turns out to be important. So what happens when you put the atoms in the cavity? So the problem of phase shift turns into a cavity resonance frequency shift. So everything boils down to measuring the cavity resonance frequency shift, which tells you the population, essentially the JZ, the population difference between the atoms. So we stabilize our 1560 nanometer light to this cavity. This cavity is 4 kilohertz line width. It's rather narrow, and we stabilize it down to 4 hertz RMS in the bandwidth of the cavity. And then we generate the 780 nanometer light that's probing the cavity by frequency doubling this 1560 nanometer light, so it's automatically stable with respect to the cavity resonances. And we have a technical noise floor corresponding to reading about 3 atoms worth of cavity frequency shift out of 1 million. All right, so the problem I said is now measuring the cavity resonance frequency, and the way we do this, we use homodyne detection. We get the 780 nanometer light, split it into two. Part of it goes to the cavity and comes back. Part of it goes through this upper path and interferes on this last beam splitter to give you an interference signal. There are some additional AOMs in this picture that are used to create sidebands that go to the cavity to stabilize the path lengths between the cavity and your homodyne system. So it's a joint homodyne heterodyne system that both stabilizes the path lengths and measures the cavity resonance frequency. And at the end of the day, what you get is a DC signal out of your system that's linear in JZ, the population difference, in a certain range of frequency. So if you can measure this voltage, you know what your population difference is, and then you're good to go. So one unusual characteristic of the system is that we're shot noise limited from 10 hertz all the way out to 5 megahertz. This is not very typical. Oh, the relevant bandwidth in our experiment is about from 100 hertz to a kilohertz or so, because we don't, the cavity line width is 4 kilohertz. We want to be able to load light into the cavity, but we don't want the experiments to take much more than 100 milliseconds or 10 milliseconds or so, that's its time scale. So we want to generate squeeze states. How good of squeeze states can we generate by doing these measurements? So then the question is, how well can you resolve this JZ using the cavity? So there are two main factors that go into this. The first one is a competition between two noise sources. One is photon shot noise and the other one is spontaneous emission, followed by spontaneous Raman scattering, which I call spin flips. So the more photons you send in the cavity, the better you can resolve the frequency, but the more photons you send in, the more spontaneous emission you cause, giving rise to a random walk in the observable you're trying to measure. So there's an optimum point where these two balance each other, so there's going to be an optimum amount of light that you need to send in. And there's a second effect, is a saturation effect, where the more atoms you have, the more scattering you have out of your cavity, which broadens the cavity line width and makes your measurements not as sensitive. So at optimal points, once you optimize everything, it turns out you should be able to get 28 dB squeezing if you didn't have any optical losses, but we have only about 16% collection efficiency, which brings us down to 24 dB. In theory, we should be able to get that much squeezing. All right, here's what the experiment looks like in the lab. It's a rather compact experiment, so this black box is where most of the magic happens. If you look inside closely, here's our experimental vacuum chamber, and here more up close, it's made out of zero-dur glass. It has very low thermal expansion coefficient. It's all monolithic, so everything is under vacuum. These two are the mirrors. We load in magneto-optical trap in the center of it and send the light in from either this side or that side to trap the atoms or probe the atoms. All right, so let's talk about some results now about squeezing. Okay, there are three pillars to establishing that you have squeezing. One is that you really need to know what your shot noise level is, otherwise you wouldn't know whether you're squeezed or not, and this historically turned out to be problematic to identify your shot noise exactly. So here's what we do. We get the atoms inside of the trap, and we send a microwave pi over 2 pulse to bring the atoms on the equator of the Bloch sphere. And then we send in a 200 microsecond pulse to the cavity optically to measure the cavity resonance frequency, which tells us what the JZ is. And we go ahead and make a distribution of those measurements. Here's a sample distribution taken with 200,000 atoms. It's pretty Gaussian. And here, this plot shows as a function of atom number what the JZ noise is, and it goes indeed as the square root of the number of atoms. And this black dashed dot curve is the theoretical expectation. So we have shot noise under control. All right, pillar number 2 is that you need to show that once you make a measurement, you indeed have lower noise than you started with, lower noise than shot noise. So the way to verify that is you make one measurement after you make your first measurement, and then wait and make another measurement to see if it tells you the same value or not. So we use two equal strength measurement pulses for this. So this pi here stands for we use it as a proxy for the intensity of the light. Pi means that amount of light causes pi worth of an AC Stark shift phase on the AC Stark phase shift on the hyperfine states. So we make one measurement and go ahead and make another measurement and see if the two are correlated. So I told you that there's a competition between shot noise and spin flips. The amount of light you send in and the amount of spontaneous emission you get. So this is a plot for, as a function of measurement strength and how much light we're sending into the cavity, how much noise we're getting. So different curves are different atom numbers and they all behave the same way. As you increase the amount of light that goes into the cavity, the back-to-back measurement difference noise goes down further and further, so you're resolving the quantity you want to measure better. But there's a turning point where spontaneous emission caused spin flips take over and do harm. So if we go ahead and plot the optimal points here, you see that as a function of atom number, as the atom number increases, you get better and better reduction in noise with respect to shot noise. At one point, the absorption becomes too large and measurement resolution goes down and you don't want to go that far. All right, so the last pillar is, now we have demonstrated that we have noise reduction. Last pillar is that you need to show you have coherence, otherwise you don't have any signal to work with. So, and to do this, all you need to do is prepare a squeeze state and execute either Rabi or Ramsey oscillations to see what your fringe contrast is. And for a properly chosen intensity, we get about 96.2% of fringe contrast, which means that the prepared squeeze states indeed do have coherence. The length of the block vector is 96.2% of the original 99.8. Thus, you have coherence. And if you put in some numbers, you see that at 500,000 atoms with this chosen probe strength, you have, including the loss in coherence, you have 20.1 dB worth of squeezing in the initial states that you have prepared. This is the largest squeezing observed, of course, to date. And the question now is, how much of this can we use for a metrology experiment? Here is a very simple metrology experiment. What we want to do is we want to prepare a squeeze state and make a little bit of a rotation of that state by applying a microwave and see if we can tell the difference between those two squeeze states that are slightly displaced with respect to each other. And in numerics, we apply basically 660 microradian of a rotation on the block sphere to see if we can tell this apart. And here's what the distribution looks like if you did not have squeezing. This is roughly so this is with 650,000 atoms. This is roughly the shot noise distribution, a little bit larger at large atom numbers. And here are the results with squeezing. So this corresponds to this state. This corresponds to this state. So we're basically being able to read all the way down to 140 microradians RMS in a single shot. If you did not have entangled atoms, with independent atoms, you would have required 70 times more atoms to be able to get to the same resolution. And we do not lose much. Basically, we get 18.5 dB metrology improvement. We started with 20, and we were able to use 18.5 dB of the squeezing to demonstrate a metrology example. We went ahead and did a very simple clock measurement as well. We did not build a full glory clock, but what we did is we made a phase comparison between our microwave local oscillator and our atomic system. So for this, we take these JZ squeeze states, and as I was telling you earlier in one of the first slides, we rotate it into phase-sensitive position with a microwave rotation. And then we let it sit there for this example, 220 microseconds, and then convert it back to population. So then any phase shift accumulated during the wait time will be mapped onto the population difference, and now you can read it below shot noise. So for this experiment, it turned out that our atomic system was way too sensitive, so we needed to lower in comparison to our microwave local oscillator noise. So we needed to lower down the atom numbers down to 100,000, and so we worked with 10 dB squeezing in order to not lose. So we lowered the atom numbers to not lose the squeezing, otherwise we were losing the squeezing since the microwaves were very noisy in comparison to the atoms. So here's what we get. The blue data set, so this is a fraction, this is essentially an Ellen deviation graph. It tells you this fractional stability of the local oscillator between the local oscillator and the atom. So we converted it into frequency. Sorry, the frequency, fractional frequency stability. This is without squeezing. So this is right at shot noise. This is, you average down as 1/the square root of the time. And with squeezing, you average the same way, but you start at a lower initial fractional stability. Essentially, this buys you a factor of, so this gets you a factor of 10 or a factor of 11 gain in your averaging time using this squeezing. All right, so how well are we doing in squeezing? So I have a plot here that collects together a variety of different measurements and with different methods that systems that have demonstrated squeezing. There are two messages. One, we're doing well. Two, it's non-trivial to do well. So there are so many results out there that have run into many problems. These are all different kinds of experiments, not necessarily on the measurement base. Some of them are BEC interaction based, some of them are measurement based, some of them are cavity based, some of them are not cavity based. So in the last part of the talk, I want to, so as you see, there's a problem that people are not being able to do these measurements very well. You're not being, there's something non-easy about going down, making measurements below the standard quantum limit. So in this last part, I'm going to tell you about a new idea and a new implementation, what we call quantum phase magnification. So the main problem is that the detection noise so we want to generate squeeze states, but it's not easy to measure below the standard quantum limit. So the bottleneck in all of these experiments that I have plotted in the previous slide has been the detection noise problem, one way or the other. So the question is, to do quantum metrology, do we really have to make measurements below the standard quantum limit? It sounds like a silly question, and the answer is going to be, turns out, no, you don't really need to be able to resolve your quantum states below the standard quantum limit to do useful quantum metrology. In fact, you can bring the noise levels up to measurable levels. So what I'm going to show you is doing quantum metrology without ever having the measurement sensitivity to make any measurement below the standard quantum limit. So here's the idea. We want to somehow magnify these states. So let's say we want to distinguish two coherent spin states on the Bloch sphere, so they're separated from each other a little bit. Can we tell the difference between these two? If our detection system is not good enough, we cannot. But what we can do is to generate interactions to somehow distort this distribution on the Bloch sphere. So this necessarily requires nonlinearity and interactions between atoms. So that we can actually go ahead and make measurements with low quality detection systems, and we can still observe this separation between these two states. I'll first tell you about the coherent state case, then I'll very briefly mention that we also do this with squeeze states. So for this part of the talk, we're not going to need to think about a Bloch sphere. We can just focus onto a small region on the Bloch sphere, so everything is on the plane now. So this is your typical phase space of optics or mechanics. So we want to tell the difference between these two states that are separated by this unit I called S. So how do we generate these interactions that are supposed to do this magnification process? So I told you that we have a trick with the cavity. We can measure the population difference. Now we have another trick with the cavity, that we can generate effective interactions between atoms. And the way this works is the following. So I told you that the cavity resonance frequency is dependent on the population difference. So for each population difference, these JZ values, the center of your resonance is at a different place. So if you go ahead and put light off resonance from your cavity, corresponding to each of these population differences, you get a different amount of light inside of your cavity. So this is kind of a nonlinear interaction that acts back on the atom. So the number of the population difference changes the intercavity intensity, and different intercavity intensities give rise to different AC Stark shifts on the atom. So population difference on the atoms give themselves a different kind of AC Stark shift depending on the population. So it's kind of a loop. So you essentially get this atomic phase shift proportional to the collective population difference. And here we go. So we're going to use this interaction to do this magnification process. And this magnification essentially leads to a shearing in phase space. And what it does is it takes your two distributions and it shears it just like this. And your initial separation S gets in the JZ direction, the population direction, gets mapped onto the JY direction, which is the phase direction, with a magnification factor of M. So note that this is simply analogous to the free expansion of a gas, because after all, we're realizing like a P squared Hamiltonian. So if you just think JY is position and JZ is momentum. So you go ahead and do a last rotation and map this phase onto population difference, and essentially you have magnified your states. And you go ahead and make a measurement that is not very sensitive. So for our non-sensitive measurements, we choose to do the measurements with just fluorescence imaging as opposed to cavity measurements. We just turn off our lattice in the cavity and then image the atoms with fluorescence imaging, which has a pretty bad noise floor of 15 dB above the standard quantum limit. And we simply resolve these two coherent states, coherent spin states, as I will show you now. So what we do is we compare the measurements to show you that this protocol is actually working. We make these measurements first with the cavity, and we obtain histograms and what these states actually look like. So these are the two states that we toggle between. We go back and forth and obtain the distributions of these states using our clean, precise cavity measurements. And then implement the magnification protocol here with a magnification of 45, and then make a fluorescence measurement to see what the distribution looks like. And if you look at it, the signal to noise looks pretty much the same. And essentially, the protocol is working. So the larger your magnification here, the better you preserve the signal to noise ratio between these two states. So these are quantum limited states. They are both coherent spin states. They are both at the shot noise, and this is just a 45 times magnified version of that. So here I have plenty of time. I was just going to skip this quickly, but I can actually tell you more about this. So now we want to apply this to squeeze states. There's one problem with that we are now mapping the population difference. We're mapping JZ onto JY. But with squeeze states, you have a lot of noise on JY to begin with. So in order to tell two squeeze states apart from each other, you need more and more magnification to really separate these from each other, so that you can resolve it. So there's an easy trick that you can do. You make a little rotation of these states initially on the Bloch sphere. So these are all microwave-induced rotations on the Bloch sphere. And then do the same procedure, and it turns out that you can get an optimal separation of the states at a chosen magnification value. So you don't really need to use more and more magnification to tell apart two squeeze states. So this is very much analogous to the action of a lens on a beam of light. the math is identical as a matter of fact. Now I want to demonstrate this experimentally to you. And to do that, we need to first prepare squeeze states one more time. But this time we cannot use measurements because I told you that we're going to do quantum metrology without ever measuring below the standard quantum limit. And this shearing mechanism gives you a squeeze state as well. If you just start with a coherence state, you just shear it out and you rotate it, you end up with a squeeze state. We get up to 8 dB squeezing this way. The measurement method is a lot more forgiving. It works better. This is a lot more sensitive to control parameters. So this is 8 dB is the best squeezing we can get currently using non-measurement based methods. And let me go back now. And here's the experimental side of the coin. We again prepared 8 dB squeeze states, and we have 2 of those separated by the amount, S, that I told you earlier. And we want to see if we can, this is again a cavity-based measurement. We can characterize squeeze states very well with the cavity, but we want to see if we can get the same performance with just magnification followed by fluorescence imaging. And as you magnify the states, at an optimum point, these 2 states separate from each other with the same identical signal-to-noise ratio, and if you keep magnifying it, they blur into each other. So at an optimal point, you essentially recover the original separation between the states with the same signal-to-noise ratio level. All right, so to summarize, on the one hand, we demonstrated the best squeezing in any kind of physical system, and to the best of our knowledge, this is the first time a quantum metrology measurement has surpassed what's best available out there in terms of a single-shot phase sensitivity. Despite the lower atom numbers of 500,000 or a little bit over 500,000, to our knowledge, we're getting the best single-shot phase readout sensitivity. Typical atom numbers in these best engineered sensors do not really exceed several million because of systematic shifts and collisional effects. So that's why we're being able to surpass those. And on the other hand, we showed that, in fact, low noise detection is not a necessity for quantum metrology, which might improve many other experiments that are out there who are trying to do quantum metrology. So in the near term, what we want to do is release these atoms from the lattice and do a simple atom interferometry demonstration where we actually separate the paths of these 2 states and then combine them and do this atom interferometry with squeeze states. And the long-term goal at Stanford is to integrate these methods into the 10-meter atom interferometry tower, which is trying to do tests of equivalence principle. So you can get further information in these references, and I thank you for listening.